Hello again, it's Mr. Catwan here, and I'm going to present the second lesson that deals with optimization. Now, we're now going to deal with three-sided figures, and today we're going to focus on rectangular-based prisms. So remember in the last lesson, we looked at minimizing the perimeter and maximizing the area dealing with rectangles, which is a two-dimensional figure. So today we're going to look at three dimensions and how we're going to approach optimization dealing with rectangular-based prisms. So let's get straight to it here. So when we're looking at the two things we're going to look at today, we're going to look at minimizing the surface area and maximizing the volume. So we're now looking in three dimensions, and we're going to discover something when it comes to the measurements dealing with the optimization of the surface area and the volume, that certain conditions do exist with rectangular prisms. So let's go straight to it. Now, before we begin here, let's reintroduce ourselves with the calculator, because we're going to do something very brand new for you here in terms of what keys to press to solve for the things that we're doing. So everybody's familiar with taking the square root of something. And today what we're going to do here is we're going to discover something called taking the cubed root. And basically what we want to do here, we're going to look at special formulas over here. And the first formula we're going to look at here is the fact that we're going to be given a volume, okay, where the volume is maximized, and what we want to figure out are the measurements that's going to minimize the surface area. Okay, and as you can see, the first formula we have here is V is equal to S cubed. So we're going to go through the steps in detail in terms of how to solve for that S using the keys in the calculator there, all right? And basically what we want to do here is discover what it means to take the cubed root. And then from there, once you find the number of the measurement of each side, we're going to calculate the surface area using another special formula, which is the surface area of an optimized rectangular-based prism. And what we need to do there is take the number of faces and then multiply it by the measurement of the sides squared. Now you're probably thinking, well, how do we know how many, what the number of faces are for a rectangular-based prism? Now, for any rectangular-based prism, okay, where all faces are enclosed or they're there, just think about a box for a moment. If you have a box, which is a perfect example of a rectangular-based prism, okay, you will discover that there are 6 faces, okay, the top and the bottom, okay, the 2 sides, okay, and then another 2 that make up the front and the back. So that's a total of 6. So the number of faces for any rectangular-based prism, provided that all faces are there, is going to be 6. All right. Okay, let's get straight to it. And again, the first thing we're going to do here is to go over the keys in the calculator. And what we want to do here is to take a look at the x cubed key. Now, we did a lot of this when we were dealing with exponents, but we're going to do something different with it in today's lesson. And basically what we're going to do here, again, is to review how we can use this. And all we need to do with the x cubed key is it cubes any number that you put in. So for example, if you take a look at 4 cubed, okay, so you press 4, okay, and then you press x cubed, okay, that will give you an answer for that. Okay, now that's pretty straightforward there. All right, so the next thing what we're going to do here, we're now going to take a look at taking what's called the cubed root, okay, and then from there we're going to press 2 buttons here, which is the second function and that x cubed key that you pressed just a few seconds ago. And the way you do that, okay, is to take a number, and what it's going to do here is take a cube root of the number that you put in. And the way we're going to do this is, if we want to find the cube root of 125, just press the following steps, or press the following buttons. Okay, press the second function, okay, press the x cubed button, and you notice that when you press the second function in the x cubed, okay, you get a little 3 in the top left there with a sign, the root sign there, and then we put 125 and press equals, you should get a value there of 5. All right. Okay, so now that you've discovered what keys to press in the calculator, okay, let's take a look at some examples here. All right, so it says a cardboard box has a volume 1,728 cubic centimeters, and determine the dimensions of a square-shaped box that will minimize the amount of cardboard used here. Now you notice that the key word here is the word minimize, okay? And anytime you hear those words over here, that's you need to use the special formulas that you were introduced to at the beginning of this lesson. So step number 1, we're going to use the formula for the optimized volume in this case, which is V is equal to S cubed. Okay, and that's going to give us V is equal to S cubed here. And all we're going to do here is take the 1728 and then replace it in for the V. Okay, and when we do that, we're now going to, in your calculator, Okay, you're now going to take the cubed root of 1,728. So start off by pressing the second function key, the x cubed key, and then punch in 1,728. And when you press equals, okay, you should get 12, okay, or in this case here, 12 centimeters. All right. Now it says, using the measurement from A, how much cardboard will be used to make this box? And we're going to use the special surface area formula. Okay, so surface area equals the number of faces times s squared. So remember that for a rectangular prism where all faces are present, okay, that's going to be 6. Okay, so we're going to take 6 and then multiply it to 12 squared, and that's going to give us 864 square centimeters. All right, and that's all there is to it. Okay, let's do another one over here. And the next thing we're going to do here is do the same thing, use the same formula. Okay, so you can see here, it says determine the interior measurements of the container with a volume of 3,869.893 cubic centimeters. Again, same approach. We're going to use the formula for the optimized volume. Now you're probably wondering, how do we know to use the volume or the surface area formula for these type of problems? Okay, always look at the given measurement. So you can see in this question over here, it gives us a volume. So since a volume is given to us, okay, automatically write down the formula for the volume, okay, where the volume is optimized. All right, and just like the previous example, we're going to replace the 3,869.893 in for the V, okay, and then from there, take the cube root of that. Okay, and we take the cube root of that number, it's going to give us 15.7 centimeters. All right. Okay, so that's what you need to do there to figure out the length of the sides where the volume is maximized, okay, and the surface area is minimized. Now, in the next the next example we're going to look at, we're going to work in the reverse here, where you're going to be given a surface area, and then from there we're going to figure out what the volume is. All right, so in this case over here, what we want to do here is understand that we're, again, same type of problem, just we're now going to use a special surface area formula here. So when something is optimized, okay, meaning that the volume is maximized and the surface area is minimized, okay, what we're going to do here is that if a surface area is given to you, we're going to use the formula surface area is equal to 6s squared, and we're going to solve for that s using a sequence of steps. Okay, and from there, what we're going to do here is that we're going to solve for the s, and we're going to use that s to figure out the volume. Okay, and using the volume formula that we used in the previous question. Okay. All right, so if you take a look at the example we're going to see here, it says determine the dimensions of a square-based prism that has a surface area of 25,350 square centimeters. So since a surface area measurement is given to us, we're going to use the formula for the surface area where it's optimized. And the formula for that is surface area is equal to 6s squared. Now, what we want to do here is, in the first step, is to replace the SA with the surface area, the value for the surface area. All right, so that's step number 1. Now, what we're going to do here is something that we did based in the algebra in chapter 4 over here is we're going to isolate the S. Now, one of the steps that we're going to use here is a step that's very familiar to you especially from the previous chapters here, is we're going to take the square root. Now, remember back in chapter 4, the step where you take the square root is always the final step. So what we're going to do here is that we're going to isolate the s first, okay, ignoring the exponent 2. And the first step we're going to do here is we're going to divide both sides here by 6. Okay, and the reason for that, as I mentioned before, is that the square root step is always the final step. Now, when we do that, the 2 6's on the right side cancel out, and we get 4,225. Now, in this step, we take the square root of both sides, okay, and we discovered that the measurement for this square-based prism is going to be 65 centimeters each. All right. Now, we're going to take this S over here and then figure out what the volume is for this square-based prism. And all we need to take there is 65 and then cube it. And when you do that, that's going to give me 274,625 square or cubic meters there. All right. And that's pretty much it. All right. So that wraps up this lesson here, and I'll see you in the next one.